Hello everyone, my name is Zhao. Today I'm going to be speaking about HAEPG, an automatic multi-hop exploitation generation framework. This is joint work with my colleague Wang and my supervisor Gong Xiaorui from the Institute of Information Engineering, Chinese Academy of Sciences. In the beginning, let's see the troubles an attacker encounters when exploiting a heap-based vulnerability. First, the heap region is hiding behind the program. We cannot directly operate the data on the heap region. Instead, we have to reverse the program and figure out how it interacts with the heap and how to control this process. Second, sometimes we have to learn the mechanism that the heap allocator uses to allocate and deallocate heap objects. It could be very complicated as developers consider efficiency and safety when designing allocators. Third, even if you are an expert in allocators, manipulating the heap layout is not easy and can drive you crazy. This is a general workflow of exploiting a heap-based vulnerability. In the first step, we may need to manipulate the heap layout before triggering the vulnerability. We need to find a victim object with sensitive data like function pointers, such as the victim object shown on the screen, and put it on the position that the vulnerable data can affect. Then we trigger the vulnerability and corrupt memory with vulnerable data. If the vulnerable data cannot corrupt any useful data, we have to propagate the vulnerable data to corrupt more memory, as shown in the step 3, until we have controlled the function pointer in the victim object. And at the last step, we can hijack the control flow by dereferencing the pointer. Okay, let's see the process of exploitation from state machine's perspective. It starts from the initial state, the green dot on the left. By manipulating the heap layout, it will go through some intermediate states, which are marked with yellow dots on the step 1. Everything is still fine for the program as we just do normal functions of the program on this stage. Then on stage 2, we trigger the vulnerability and its state is red dot. From this stage, we must be careful as we corrupted memory. The program may behave oddly. In other words, it turns to weird machine. To propagate vulnerable data, we have to keep driving the program interacting with the allocator. Note that the program and allocator may not act as expected, and it is easy to fall into crashing states in this stage due to memory corruption. If we are able to propagate vulnerable data to sensitive locations without crashing, we can reach an exploitable state. Existing solutions, including Gloom, Fuse, and Slake, assume that there is a sensitive pointer that could be overwritten by merely heap layout manipulation and triggering vulnerabilities. So there is no need to manipulate heap layout after triggering vulnerabilities. In other words, they focus on stage 1, 2, and 4. We will utilize a fuzzing technique to explore states derived from corrupting states. However, it is not efficient sometimes as the search space is infinite and exploitable states are rare. So there are two challenges we have to address. The first challenge is exploring the power of heap vulnerabilities with limited capabilities. If we can corrupt sensitive data directly by triggering vulnerabilities, then there is only one hope between a corrupting state and an exploitable state. We call it single hope exploitation. Otherwise, we have to improve the capabilities of vulnerabilities. We call this process multi-hope exploitation, which means there are multiple hopes between a corrupting state and an exploitable state. As we said, it is not easy as after triggering vulnerabilities, the state of the program becomes weird machine. An attacker has to dive into the implementation of allocators and find a way for multi-hop exploitation. It requires much time and energy. Luckily, security experts summarized exploit techniques for exploiting heap-based vulnerabilities, such as unsafe unlink and fast bin attack. These techniques are powerful and general as they related to allocators rather than applications. There are a few solutions that can discover exploit techniques automatically, such as HAEPG and HAEPG. Unfortunately, they cannot use them to generate exploits for vulnerabilities. The second challenge is modeling heap interactions between programs and heap allocators. The solution which toward interpreter or kernel explore the heap state space with knowledge of language grammars or kernel syscalls. However, there is no such standard input protocol for applications, as each application parses input differently. To construct an exploitable state, we have to recognize heap interactions and assemble them in a particular way to generate exploits. Therefore, we propose HAEP to solve the challenge above. Given a program with heap-based vulnerabilities and crashing inputs, it attempts to achieve the execution of arbitrary code through multi-hop exploitation. HAEP models the heap interaction with function passes and heap primitives. Then it collects runtime information in programs when executing crashing inputs. It inspects vulnerable objects and analyzes the type of memory corruption as well as the size of corrupted data. Furthermore, we studied manual multi-hop exploitation techniques for heap vulnerabilities and designed a templating language to abstract multi-hop exploitation techniques as exploit templates. HAEP uses them to achieve an arbitrary execution and generate end-to-end exploits. Next, I will explain how modules of our system work. A function dispatcher is a code structure that is widely used in programs for function distribution and usually implemented as if-else or switch case structure wrapped in a loop. We define the basic block sequences from the loop entry to the loop exit as function passes. First, HAEP constructs the CFG of the target program. Then it extracts the function dispatcher from CFG as well as its function passes. Next, we execute function passes dynamically. We symbolize all input bytes and tracks instructions interacting with the heap region. If any attribute of heap primitives are symbolic, HAEP will record the range of it. With state analysis, we are able to reason about the relationship between heap primitives. The relationship helps us find the right heap primitives that can deallocate or edit a heap object allocated by other primitives. So why do we model heap interactions in this way? Because function passes and heap primitives are building blocks of exploitations. By assembling function passes, we are able to navigate the control flow of execution. By controlling the attributes of heap primitives, we are able to control the data flow. Therefore, we can transform the state machine in this way. And then I'm going to introduce the method our system uses to analyze vulnerabilities. First, we obtain crashing inputs with AFL. We dynamically execute the crashing input and tend return pointers of allocations. Then our system propagates the tag to the pointed memory object's bytes. The tags have three status: Initially, they are uninitialized, and instructions writing to the object will change the status to busy, while instructions releasing the object will change it to free. Before changing the statuses of them, we check if any of the violation rulers is triggered. We designed 5 violation rulers as shown on the screen. In this way, we are able to detect double free, UAF, overflow, poison, non-byte, and off by 1. Now we modeled heap interactions and detected vulnerabilities. It's time to generate exploits. The challenge is how to leverage exploit techniques in an automatic system. The direct way is to hard-code these techniques into our system. However, this method is inflexible and hard to extend, as users need to understand the deep principles behind our system when adding a new technique. Therefore, we developed a templating language to describe exploit techniques and use them to guide exploit generation. The code on the right of the screen is the template of an unsafe unlink. It consists of the necessary heap primitives for launching an unsafe unlink attack, and we call them backbone primitives. Only backbone primitives are not enough, as even slight changes in the target program result in need of vastly different exploitation strategy. Thus, the template also describes the shape of intermediate states, and we call them layout constraints. We use templates to guide the construction of intermediate states. Firstly, we traverse the backbone primitives of the template and scan all function passes to find the ones containing the backbone primitives. Then we sort these function passes based on the dependencies between them and solve the fields of heap primitives according to the template. At last, we combine these function passes together with the heap primitives as an attack sequence. The initial attack sequence may not lead to an exploitable state because it may fail to construct correct intermediate states. So we have to check if these states meet the layout constraints of the template. We dynamically execute the target program and the attack sequence and record heap layout at runtime. Once precedent of backbone primitives of a memory state are finished, we will check if the current heap layout meets the layout constraints. We developed 2 methods to assess an attack sequence. The first method is heap simulator. The main part of the simulator is a loop that wraps the 3 heap primitive functions. It takes heap primitives as the input and executes the corresponding functions to simulate the heap interactions of the target program. After finishing the execution of each function, the simulator will output its heap layout. We use it to simulate the intermediate states of the target program. The heap simulator is fast, but it lacks of runtime information of the target program, so we use it to pre-filter attack sequences. The second method is to use S2E to execute the attack sequence. We force the program to execute along the function passes of the attack sequence and transform heap primitives to data constraints and attach them to corresponding memory and registers. At the same time, we monitor the runtime memory and check if they meet the layout constraints. Only after the attack sequence passed the heap simulator assessment, HAEP will use S2E for an accurate assessment. If the layout constraints are met, the program will enter an exploitable state, and we would attempt to generate an exploit. Otherwise, HAEP will find the conflicting heap layout It infers the reason for the conflict and attempt to correct it. In general, the reasons for the conflict can be summarized as following situations. The first situation is heap chunk A should be free, but it is busy or uninitialized. In this case, we insert a path into the text sequence to release the chunk A. The second situation is heap chunk A and B must be adjacent, but there are other busy chunks between them. We solve it by insert deallocations into the attack sequence to release these chunks. If these chunks are not removable, we will allocate a heap chunk with the same size as chunk A before the allocation of it to get a new heap layout, which might lead to a satisfying heap layout. The third situation is heap chunk A and B must be adjacent, but the adjacent chunk of A is free. This is generally caused by extra heap chunks of the free list, which make chunk B gets allocated on a wrong slot, and HAEP fills extra chunks by allocating chunks with the same size as B. Finally, HAEP generates a new attack sequence and repeats the assessment and the correction. Once the attack sequence passes the assessment, HAEP executes it using symbolic execution and detects if the data on the important location are symbolic. This location including the data and the address of memory write, function pointers, and so on. The symbolic data of different locations will give us different exploit primitives, as shown on the screen. Our strategy is to transform other exploit primitives to an arbitrary execution and hijack control flow with one gadget to spawn a shell. In the end, we solve constraints collected when executing the attack sequence and generates an exploit input. We evaluated our system with 24 CTF challenges. We selected challenges based on the following rules. First, programs must have at least one heap vulnerability, and vulnerabilities are diverse. Second, programs with higher scores are preferred. In general, challenges with higher score are more difficult. We implemented a prototype of HAEP and wrote templates for 4 common heap exploitation techniques. As a result, our system accurately reasons about the type of vulnerability for 21 programs successfully and generate working exploits for 16 of them. It solves extra 2 challenges after downgrading the version of glibc. Our future work is to introduce more exploit techniques into our system and adapt it to real-world programs. Okay, this is the end of my talk. Thank you for your attention. And if you have any questions, please do not hesitate to contact me. Thank you.